By the late 19th century, the laws of motion and electromagnetism worked perfectly. Light appeared to be a definitive, continuous, unbroken wave. But measuring the glow of a hot object created a massive problem. If you heat iron in a forge, it glows dull red, then orange, then white hot. Physicists tried to calculate how much light energy that object should emit across different colors, using those established reliable laws. The math returned a catastrophic answer. Because a continuous wave can be divided into smaller pieces infinitely, the equations predicted that energy would skyrocket as the wavelength shortened toward the ultraviolet end of the spectrum. According to classical physics, a simple warm oven should drench you in an infinite, lethal blast of ultraviolet radiation. This graph shows the divergence between theory and reality. The gray Rayleigh-Jeans line rockets off to infinity, while the blue Planck curve shows what actually happens. The energy peaks and then falls back to zero. Physics was predicting a lethal, impossible universe. This anomaly signaled that the rules of the universe were broken at their most basic level. In 1900, Max Planck attempted to force the math to match the measurements. He later called his approach an act of desperation. He wasn't trying to change physics. He was trying to tweak a formula so the energy curve would match the data without going to infinity. To make the equations balance, Planck proposed a new rule. Energy cannot flow as a smooth fluid. It must be traded in discrete, indivisible chunks, like paying for an item with individual coins. He called these distinct packets quanta. Planck did not believe light existed as physical grains. He viewed these quanta as a mere mathematical trick until a proper theory could be found. He plugged the hole in the math, but he left a ticking time bomb for the scientific community. If this grainy math reflected the physical nature of reality, then every classical assumption about the universe was wrong. While theorists argued over blackbody radiation, a new experiment, the photoelectric effect, exposed another flaw in the wave theory. When you shine light on a metal plate, it knocks electrons loose, creating a current. But the data from these sparks defied the laws of waves. The first impossibility was the threshold. A faint ultraviolet lamp frees electrons instantly, but a blindingly bright red spotlight frees absolutely nothing. If energy builds up like a wave, that intense red light should eventually shake an electron loose. In the lab, it never does. The second impossibility involved the energy limit. Making the light source brighter increases the number of electrons knocked loose, but it never increases their speed. The departing electrons fly away with a maximum kinetic energy that stays the same no matter how intense the light becomes. The third problem was timing. Electrons pop off the metal the instant the light hits. A continuous wave would need time to wash over the surface and accumulate enough force to break an electron free. A continuous wave model cannot physically produce these results. In a laboratory, the wave theory of light had officially died. In 1905, Albert Einstein gave Planck's grainy math a physical body. Light travels as a hail of discrete, localized bullets. Einstein modeled this as a one-to-one impact. One individual photon hits one individual electron, transferring all of its energy in a single instant. To break free, the electron has to pay a minimum energy toll called the work function. If the photon brings more than the toll, the electron escapes. If it brings less, the electron stays trapped. This perfectly explains the laboratory data. Adding more red light just results in more small photons failing to pay the toll. But a single ultraviolet photon is large enough to pay the fee at once, explaining why it frees the electron instantly without a time delay. Einstein proved the grainy math was no trick. Light itself was quantized, an insight that rewrote our understanding of reality and earned him the Nobel Prize. Lingering skepticism remained into the 1920s. Scientists demanded physical proof that light possessed particle-like momentum rather than just trading energy in chunks. This diagram shows Arthur Compton's 1923 experiment firing X-rays at electrons in graphite. He wanted to see exactly how the light would bounce. The X-rays bounced off, lost energy, and lengthened their wavelength. The momentum transfer was exact and physical, occurring as if light and electrons were billiard balls colliding on a table. This undeniable physical collision ended the debate. Regardless of how it spreads through space, light definitively exists as a physical particle. Human understanding had shifted. At its most fundamental base layer, the universe is not a smooth, continuous fluid of energy, but a discrete and grainy reality. The classical world shattered when physicists finally looked at the individual pieces. This era taught us that when our intuition conflicts with laboratory data, the data must win. We had to surrender our common sense to the hard evidence of the experiment. Following that evidence is exactly what paved the way for lasers, semiconductors, and the modern world of quantum computing. The strangest features of our universe are not theoretical fantasies. They are inescapable truths forced upon us by the undeniable reality of experimental evidence.